Okay, welcome, Michaela. It doesn't seem as if anyone else is coming, at least not for now. So I'm going to go ahead and go through the solutions for the assignment so you can be ready for your test, which they postponed to Monday. So those who aren't here, hopefully they can watch it in time to get the test on Monday. The test was supposed to be today. Because I wasn't here Monday, I'm going to get some extra time to study, which is putting the test to Monday. All right. So let me get through this. Okay. Now the first question on the assignment, let me pull it up, was that one easy. I think that's even the notes, I look at it. Go to number 2. So number 2A. Oh, hold on, Anthony's calling. Hey, you're correct, Lafern. He's having difficulty getting in. Where Michaela gone now? What is this? Wait, it says that she's joining. Okay. She comes back. Come on, Michaela, come on. Okay, I'm just giving her a little bit. If she doesn't come on, then I'm just gonna go ahead. I'll give her 1 minute. What's going on? Oh, she left. Anthony's getting in. Okay. Well, he says, as long as you have 2, we can do something. Although if Michaela didn't get back a while ago, then I'll just work with you alone. Ah, Anthony's here. So Anthony, are you hearing me?
Yeah, yes, sir. I'm using I got through my data. Those guys are fixing something on the floor. That's why.
Oh, the internet campus is down.
I'm not sure if it's the campus, but there are some guys on my floor fixing the internet wires.
Okay. All right. Yes, so we're doing number 2, part A. So 2 part A says show that 5 to the 2n plus 1 plus 2 to the 2n plus 1 is divisible by 7. All right, so we're going to show it, of course, divisible by 7 means that it's equal to some multiple of 7. Let's call it 7c. I shouldn't use c, no. I use c, doesn't it? D. I like to use the c later. You see it a lot. 7d. D is an integer. I should make a note of that. D is an integer. All right, so I'm going to prove it for n equals 1, or it says for all n greater than or equal to 0. Oh, so use n equals 0 first. I should have gone through these before. Hope I don't make any mistakes here. No. So putting in a 0, get 5 to the 2 times 0 plus 1. We always show it for the first integer, or the first possible number. And you prove it for the rest that comes after. If it doesn't work for the first, and it won't work at all. So checking to see if this is equal to 7 times some integer. So for the left side, we have that's 5 to the 1 plus 2 to the 1, which is equal to 7 times 1, because that's 7. So 7 is equal to 7 times 1. So it is true for n equal 1. Therefore, true for n equal 1. I think I saw one person make a mistake on the assignment then, because when I was looking through your assignments, if I hadn't checked the question properly, I would have marked it right, because the person started by proving it true for n equal 1. You have to check for the first number in the sequence or in the
So
list of numbers
you
below
mean
that.
so you mean true for n equals 0, 0, right?
Yeah. 0. Oh,
Okay, yeah.
yes. 1. So you used to writing 1. 0. But the person used the number 1 and actually say true for 1. I'm gonna have to. I'll give them marks still, but I'm gonna lose a 1 mark or 2 mark for that. Anyway, the next step is to assume that it is true for n equal 1. For n, assume true for n. Assume true for n. So we're going to prove that it's true for n plus 1. I assume that it's true for n. Right, so I'm going to use the next page. So anybody writing this? I think when I was glancing through, most people got this though. Yeah.
If you had it true for n equal 1, I mean if you select n equal 0 and then prove true for n equal, sorry, if you use n equal 1 instead of n equal 0, would that have been wrong?
Yes, because you wouldn't have been wrong, incomplete. You'd have proven it true for every number from 1 up, but not for the 0, which comes before. Because induction proves for every following number. Whatever number you prove it true for, and you use induction, you prove it true for every number that comes after that one as well, not before. If you use 1, you have eliminated 0. Okay. So it's not wrong, it's incomplete. You just leave out the 0.
Okay. Yeah. So you're looking at positive, so you have to prove it true for the first positive integer then, that's what you're saying?
Right, that's what you would have done if you use n equal 1.
Okay.
Because this one said n greater than or equal to 0. I think I made a mistake with part B. I said for all. Oh no, it's odd integers. I said. I was looking at it now. It's fine then. I thought I said for all integers. The note doesn't work for -1 and stuff. I said all odd. Okay, that's good. But where was I? Oh, so is anyone writing this? No? All right. I'm going to continue. We're going to assume it's true for n, which means that our statement is true, which is 5 to the n plus, oops, start over. It's not 5 to the n, it's 5 to the 2n. 5 to the 2n plus 1 plus 2 times 2 to the 2n plus 1 is some integer, some multiple of 7. So we need to prove that it's true for n plus 1, which means that 5 to the 2 times n plus 1 plus 2 times 2 to the 2n plus to the n plus 1, beg pardon. Replacing n with n plus 1. We want this to be equal to some multiple of 7 as well. Sorry, I put K right here because I want to use C last because C is easy to write. Let me see. Good. I'm going to keep writing since C all the way down. All right, so this gives us 5 to the 2n plus 3 plus 2 to the 2n plus 3. I did something like these with you before. You're gonna, the easiest way to do it is add something and subtract it, but you have to figure out what to add and what to subtract. Here's how you can figure out what to add and subtract. Look at what we have to use this in our proof. This has to be used. So you say 5 to the 2n plus 1. That's, if you multiply by 2 more 5s, then you get 5 to the 2n plus 3. So in other words, you have to factor out the 5 squared right here. You take out the 5 squared, you're left with 5 to the 2n plus 1. And you say, that means you're going to have to do the same thing for the next one. But you know, you're going to have to add and subtract and put things in. So you want to get a next term that can get you to get the 5 to the 2n plus 1 plus 2 to the 2n plus 1. Put it in there. That's what you're going to add and subtract. 2 to the 2n plus 1. I'm going to put that term in there. It wasn't there before. I'll show you a different ink, and subtract it out. 5 squared. So it's always good to look at what you want to use. That will give you an idea of what you need to add and subtract. So that's how I do it. Maybe you might have to think of it a different way. I'm not sure. Hold on, run out of space. So we still have that 2 to the 2n plus 1. I'm going to factor it out to 2 squared. 2 to the 2n plus 1. It's a bracket. It's a 1. Equal. Oh boy, I hope you guys can see that, you know. Not sure if it's equal to 7c yet. Alright, so let's read it because the left I have 5 squared times 5 to the 2n plus 1 plus 5 squared times 2 to the 2n plus 1 minus the same thing, 5 squared 2 to the 2n plus 1 plus I'll just factor this thing right here. This thing right here, factor it, give me this one right here. Just to go 2 squared, leaving 2 to the 2n plus 1. Pardon my bad handwriting, but I don't know what I needed to make it small as I go to the end. And of course, 7c's at the next side. So I'm going to finish factoring over here now. So you see that both of these terms have the 5 squared. There's one here, one here. So take out the 5 squared, leaving 5 to the 2n plus 1 plus 2 to the 2n plus 1 minus, let's have the 5 squared out there. You notice that there's a minus 5 squared and there's a plus 2 squared times the same term, the 2 to the 2n plus 1. If you want, you can actually take it out. 2 to the 2n plus 1, leaving, oops, that's a plus then. So leaving, I could leave it as minus, you know. Anyway, it doesn't matter. So now you're going to be left, I'm going to put 2, I put it, doesn't matter. Minus 5 squared inside here, plus the 2 squared. So let's factor the 2 to 2n plus 1, and we're still not sure if that is equal to some multiple of 7, which will make it divisible by 7. So on the left side, 5 squared is now multiplying the thing that we had up here, 7k. So we assume that that is equal to a multiple of 7. So this is 5 squared times some multiple of 7. So that's divisible by 7 so far. Plus 2 to the 2n plus 1. Let's simplify this now. That's 5 squared, that's negative 5 squared, that's negative 25, plus 4, that's negative 21, which is a multiple of 7. You could have actually written it right there, but I want to be clear. So the first part here, this is 7 times 5 squared times k. Don't care what the 5 squared is, don't care what the k is, so that's not their integers. 7 times the integer is divisible by 7. Minus 3 times 2 to the 2n plus 1. I factor the 7 again. You know, 7 into 21 to get 3. And that is equal to, so here the k, oh, piece and piece, the c. There's a different ink. C turn to k, c. So here we see that c is that thing in the bracket, that's the integer, and 7 times it is equal to something that can be divided by 7. So it's divisible by 7. Therefore, true for all n greater than or equal to 0. And what right? Therefore, true for all n greater than or equal to 0. Down in the space. Any questions?
Yeah, if you just had the left hand side showing that it's a multiple of 7, that would work as well too, right?
Yeah, I suppose I could do that. As long as you mention it afterwards. You see, if you do it like that, then you have to write something afterwards.
So, oh, you can say that once it's divisible by 7, you mean?
Right, so it's a multiple of 7. So if you write the equal to 7 times something, you don't have to write that. You don't have to explain it. If you just work it out on the left without saying anything, then you won't get full marks for that.
Oh, okay.
Any other question? For Norma Keeler, any writing or Anthony?
You did the part A already?
No. This part is something that I didn't work out with you for you before. When I was looking at it a while ago, I said, but this looks like something we did in class. Did you do this in class? Or is that a different one? One part A. Hello?
Oh, I was referring to the one with A union B.
Yeah, that's what I'm talking about. Was that one done in
Oh,
class?
okay.
I'm asking you, no. I'm not telling you. I'm asking if it was done in class.
I don't remember.
Then
I
I'll do it.
see you explain it. You explain what the slash means and so forth. But I don't remember
Didn't
seeing
do the
it.
proof.
I was trying to go through review the videos, but I didn't see the exact proof itself.
Let me ask the girls then.
I'm
Let
not sure
them
if
see
the
if I.
others would have seen that, but I tried to go. I go through the videos and I just didn't see any.
No, sir, I don't remember seeing the proof.
Oh, good. And that means. Because when I was glancing through the assignment, I didn't even bother to look at that because I thought I did it in class. Well, that is good. Well, okay, I can work it out then. So I'm just finish number 2 and then I'll do that one. Part number 3 in 2B. Beg pardon. Somebody's writing this. Michaela, you saying something? No? Alright. Number 2B. So remember to go back to part A to number 1, sorry. Something interesting might come up and I forget. It happens all the time. So part B. Part B. No, part B is prove that n to the 4 minus 1 is divisible by 16. So our statement for P of n is that n to the 4 minus 1 is equal to some multiple of 16. So let me use k right here. All right. So we're now going to show that it's true for all odd integers. All odd integers n. So the first odd integer is 1. Remember that n represents natural numbers. So I didn't mention that, you know. But yeah, they told you in this class that all the n's that you see are natural numbers. So you're not going
So,
to see natural
sir,
numbers.
in the previous example, 0 is the first integer.
Mhm.
But wouldn't you say that 0 is also odd and even? So wouldn't it be the first case for this one as well?
0 is not odd. 0 is even.
0 is even? I thought you
Mhm.
said it's neutral.
Yes, meaning not positive, not negative.
Oh,
Odd means, even means when you divide it by 2, there's no remainder. So into 0, there's no remainder. So odd means when you divide by 2, the remainder is 1. 2 into 0 does not leave a remainder 1. Got that?
yes,
Sir,
sir.
I was interpreting
Okay.
it as that n. I was interpreting it that n is an odd number in this case for all odd integers n.
Yeah, so n is odd.
Okay,
So
right.
start from 1.
Okay.
So 1 here will give us 1 to the 4. You started from 0, Lafern?
No, sir.
Oh, then, yeah. So yeah, 1 to the 4 minus 1. We're checking to see if it is equal to some multiple of, let's use d, on letter 1. So on the left side we have 0, which is a multiple of 16. 0 is a multiple of every number. Or every number. 0 is divisible by every number except 0. If you want proof, see it here. 0 is equal to 16 times 0. Oh, once you can find an integer that multiplies it to give a number, then yes, it is divisible. So 0 is divisible by 16, therefore it's true for n equal 1. True for the first odd integer, which is 1. Alright, so having done that, we can now check to see if it's true for other integers as well. Well, for all other integers. So assume n true for n. So having assumed that, we will now prove that it's true for n plus 1. Oops. Alright, so I'm writing 5, 4, 3, 2, 1. Oh, no, that's a mistake. I was expecting, or I'm expecting to see in the assignments. I didn't look for this one, you know. But most persons will go check n plus 1. If n is odd, n plus 1 is not odd. The next thing you have to use is n plus 2, n plus 4, n plus 6. But odd integers go up by 2. So if you had used n plus 1, you wouldn't be able to go any further. You'll see that it's not working out. Anyway, so where am I now? Statement that we assume to be true is this. N to the 4 minus 1 is some multiple of 16, which means it's divisible by 16. So hopefully we can use that statement. So we're going to go now to check what's happening with n plus 1. 2 to n plus 2. Next odd integer. Remember, n is odd, so the next odd integer will be n plus 2. Which is now going to be n plus 2 to the 4th power minus 1. I'm going to check if this is equal to some multiple of 16. It's not equal yet. And if it's equal to some multiple of 16, which is 16 times c. So we're going to expand that. So using Pascal's triangle, we have n to the 4 plus 4 times, what did I do that? Just write the 8, you know, since I write the 4 already. 4 times 2n. You know, the 4 is in the Pascal, and then n to the 3 and 2. You know what already? I don't have to explain it. And you have 6 times. I'm going to write, well, since I start but already, write the 6. And then you're going to have 2 squared, which is 4. 4. And then n squared. Then 4 again, times 2 to the 3rd, which is 8. And then n to the 1. And finally, 2 to the 4, which is 16. I'm still not sure if that is equal to, oops, forgot the minus 1. Board look messy. Minus 1. Checking to see if that is equal to some multiple of 16. Okay, let's see if I can write the next line a little better. N to the 4. Start bad already. Plus 8n cubed plus 24n squared plus 32n plus 16. There's a reason I'm leaving the minus 1. Minus 1. Checking to see if that is equal to some multiple of 16. Now, since we already, you know, whatever we use, whatever we assume to be true, we have to use it somewhere. That's why I didn't put the 15 at the end. I'm now going to combine this n to the 4 right here and this minus 1. Use our first statement, which is 16k. That's why I didn't subtract the 1 right there. So this gives us n to the 4 minus 1. All right, one part taken care of. So now we're left with 8n cubed 24n squared plus 32n plus 16. Now you can look at what we have there to determine what you can actually use already as a 16, meaning what times what give you 16 already. So you can see that we're not sure about the 8n cubed, we're not sure about the 24n divided by 16, but we're sure about the 32 and the 16. So you can just put those two aside. Let me show you what I can put aside. You see this first term here, n to the 4 minus 1. And the back foot, n, Jesus. Back up that. N to the 4 minus 1. That's a multiple of 16, that's good. Plus the 32n and the 16, those are multiples of 16. All that's left now to deal with is that 8n cubed and a 24n squared, squared. So let's focus on it a little bit. I mean, if I was proving it, I wouldn't write this step, but I want you guys to understand it in case. Maybe I'm wasting time. Maybe do it already in the assignment. Should have marked them already. Anyway, so
Which step you said you could skip, sir?
this, you didn't have to group them up like that.
Oh.
But I did it so that you guys can see it clearly. This multiple of 16, that multiple of 16. You know, factor 16 from the second one, you can see it's equal to some 16 times something. For the first one there, we assume that's true up here already. The 16k. What if I can write them down? Put them in there. This is 16 times k. That's a multiple of 16. This here is 16 times 2n plus 1. That's an that's an odd integer. Perfect. So 16 times an odd integer. Because remember, n is natural number. N represents 1, 2, 3, 4, whatever. But 16 times any number is a multiple of 16. Now this last part here, if we factor out 8, left with n cubed plus 3n squared, which is 16 times c. Now what did we assume about n from the start? Well, not assume. They told us something about n. What did they tell us about n?
Odd integer.
Odd integer. So if you square an odd integer, what do you get?
If you square an odd integer, you're gonna get odd number.
Good. And if you cube an odd integer, what do you get? Or odd number, what do you get?
Still odd.
All right. You multiply an odd number by 3, what do you get?
Odd.
Okay, so everything in that bracket is odd. But when you add two odd integers, now what do you get?
Even.
Even. Beautiful. So you see the number inside that bracket, it's going to be even, meaning it's going to be 2 times something. And when you multiply 2 times something by 8, it's divisible by 16.
Okay.
So the first one here.
Oh, sorry, go ahead. Go ahead.
The first one here is divisible by 16. See it easily. Clearly, I mean, obviously. This one is obvious as well. And this one here now is an even integer. And an even number multiplied by 8 means it's going to be at least 16 times a number, which means the number is divisible by 16. I would have written that, but then space. Okay, go ahead.
I factored out n squared and I put an explanation similar to that. But my thing is, I wasn't sure how to basically, if I could leave it just the way you have it there.
Mm.
And then, so what I did, I put a bunch of explanations
Yeah, man, that's what you're
afterward.
supposed to do. You have to explain.
You have
Just
to
leave it like
explain.
that and just, yeah, man, you have to explain that part. See, I just did
Oh,
a
wow.
while ago. You have to explain so long as I did, but
Okay.
just explain to me that it's divisible by 16. That's good. I mean, I'm also going to explain it. I'm not going to write it. I can tell you what to write, but I'm not going to write it. I just explained to you a while ago. What you didn't have to go through the n cube and the n squared and the 3n. All I had to mention was that n cube is odd, 3n squared is odd. So n cube plus 3n squared must be an even number, because when you add two odd numbers, you get an even number. And multiply by 8, it's divisible by 16. So all I had to say was n cube plus 3n squared is even, and 8 times that is divisible by 16. So it's as simple as that. Therefore, this whole entire sum, which is all of this thing right here, is divisible by 16, or is a multiple of 16.
Question though.
True for all other n. Mm-hmm.
But whether or not whatever in the bracket, whether it's odd or even, once you multiply by 8, I'm just thinking about that now. Regardless to what's in the bracket, whether it's odd or even, once you multiply by 8, it becomes even.
Yeah.
So we could have just said 8 times whether the sum in the bracket is odd or even, 8 times that, so that sum will give you an even number.
Yeah.
Okay.
But that's not what you need to prove.
Huh?
You don't need to prove it's even. You need to prove it's by 16.
That's true.
Right, so multiplying by 8 is not enough.
So that's true because right. So basically, what's in the bracket must be even.
Right. In order for it to work.
Right. That's true. Because 8 times an even number will actually be divisible by 16.
Right.
Okay.
Because that even number already has a multiple of 2, so 8 times that gives you 16 at least.
Right. Okay, thanks.
Mm-hmm. Yeah, any other questions or concerns from Lafern and Michaela? We have a lot to prove, although the rest of them are pretty short. Number 2 was the longest. Number 4 now. Not long, but you have to know what you're doing. So I only gave 2 of them. I was going to give 3 of them and I took off 1. Although in honesty, B was easy. It depends on how you do it. Anyway, anyone writing part 2? Part B of number 2? Anybody writing this? That's a question. So, all right, clear it. Let's do part C. Now, strangely enough, part C was the easiest of these 3. It looked the longest, but it was the easiest. Well, in my opinion. I was looking through the questions that I wrote. So I'm apologizing, guys. I just glanced through your assignments. I didn't mark them just to see if you guys were on the right track. Team they were. Most of you. Although your assignments came in days late, and you know yourselves. Matter of fact, only one person uploaded on time. Lafern uploaded their assignment like 1 minute after the deadline. Like, Lafern, matter they take some more time. Anyway. We won't take off any marks for lateness because I might lose some already in the marking. Just dot, dot, dot. 1 over 2n minus 1. If you guys were struggling with it, you could just email me and say, sir, give us some more time or call me up a number. If it was a general thing, I'd have given you more time.
No, I know that, sir. No, I know that.
No, you know. You knew that all along. This is not the first thing. You never asked for extension for time before. Yeah, you could do that.
I'm not sure if you ever given it.
Oh.
Anytime you take off the marks, I think I just give him the assignment. I didn't bother to take the extension.
Oh, okay.
You're strict sometimes.
No, man, but if everybody is struggling, I can't say no. If it's one person now, that's idle and whatever, but if everyone is struggling, I'll give more time.
Okay, thanks.
All right. Yeah, man. So that's our P of n. That's a statement we're focusing on. So we need to check if it's true for, you see, whenever you're given a general thing like this, notice I didn't put an n greater than 1 or n greater than whatever, let's assume natural numbers. So it starts from 1. In the question before, in part A, started from from 0. But if you're not given anything, let's use natural numbers. Because it doesn't make any sense to start from negative. You can't prove true for all numbers in the world. So unless told otherwise, it's natural. I didn't say anything here, so it's natural. So the first end I'm going to use is 1. So on the left side, we're going to have 1 over 2 times 1, 1 minus 1. You like marking all this out, you know. Yes, I will. 1 over 2 times 1 minus 1 times 2 times 1 plus 1. We need to check to see if that is equal to 1 over 2 times 1 plus 1. Well, on the left, I'm going to go straight ahead. That's 2 times 1 minus 1, which is 1 times 3, which is actually equal to 1 over 3. Let's waste no more time. Pretty straightforward to see. Therefore, it's true for n equal 1. We're going to assume, let's get as much over this side as we can, assume it is true for n. In modern algebra, you see it was n equal k, but different courses use different methods. It's the same thing. You put k is the same as n. All right, anyone writing this? All right, let's go to what we have assumed. We have assumed that 1 over 1 times 3 times, plus 1 over 3 times 5, right up to 1 over 2n minus 1 times 2n plus 2 plus 1. I'll write the n first one if I can squeeze in the 2. Not writing. Squeezing enough. So assume that this is equal to n over 2n plus 1. So for our p of n plus 1, now that was the p at the top, the p of n plus 1, we want to show that 1 over 1 times 3 up to, I think I just wrote, 1 over 2n minus 1, write it properly, 2n minus 1 times 2n plus 1. We're going to include n plus 1. I won't bother to take time with it, I'll just write it right now. 2n plus 1 is going to be 2n plus 2, right? So 2n plus 2 minus 1 is 2n plus 1. It's going to go straight to it. So it's 2 times n plus 1, that's 2n plus 2. I have the minus 1 in the bracket, so that becomes plus 1. And then 2 times n plus 1 again is 2n plus 2 plus the extra 1 in the bracket, that's 2n plus 3. Because it's so hard to write on this board, I don't want anybody to write that and then go to the next line. If you were on a regular board, I would do that. So we're checking to see if this is equal to n plus 1, replace the n's with n plus 1, over 2 times, well, I can do it here. I'm going to keep writing the same thing anyway. Now, on the left side, all of this first part here, from 1 over 1 plus times 3 plus 1 over 3 times 5 plus 1 over 5, 6, 5 times 7, you know, is always a number plus 2. Only odd numbers though. All of that is equal to this thing we assume up here. We assume that is equal to this. So all of that left side is n over 2n plus 1 plus that additional 1 over 2n plus 1, 2n plus 3. And we're checking to see if that's equal to n plus 1 over 2n plus 3. I like these induction pretty. You know what you're going towards. It's not number 4. Anyway, so down here now the denominator is obviously 2n, 2n plus 3. Sorry, 2n plus 1, 2n plus 3. So dividing into them, 2n plus 1 into that gives us 2n plus 3 times the n. Left off the n. So there's an n right here, guys. 2n plus 3. Sorry. Plus 2n plus 3 into that is 1. 1 times 1 is 1. We're checking to see if that's equal to, bye-bye, Michaela, n plus 1 over 2n plus 3. So expanding that bracket now, that's 2n squared plus 3n plus 1 over 2n plus 1 times 2n plus 3. Still checking to see if that's equal to n plus, you know what, I should have written equal now, I should have written equal. But I can squeeze it into the right. Which is going to be n plus 2n plus 3 times n plus 1. No, wrong. It's going to be 2n plus 1 times n plus 1. Yeah. Over 2n plus 1 times 2n plus 3. Which I write it right now is equal to n plus 1 over n, 2n plus 3. Because this cancels this to leave us with n plus 1 over 2n plus 3. So it is true for all n. Of course, all positive n. Let's skip a little one step where you guys could have factored it right there. You know, get the 2n squared plus 2n plus n plus 1. And then factor it to get the 2n plus 1.
And the equal sign equal sign must be under the question mark, right?
Yeah, would have been under the question mark.
Okay, all right.
Well, you can also, you mean for all the question marks I wrote? Or that's the last one?
Yes, sir. Like you have an equal sign and a question mark over it.
Yeah, you can write that, or you can actually just put the question mark. I've seen people just put the question mark. But
Oh.
if you wrote it like this, with equal under it, that's fine as well. Because it's still question if it's equal to it. Yeah.
Oh, okay. No problem.
You know why? Because sometimes, like, I don't know if I give it to you in modern algebra, but I give it to my students now, the ones in there now. Sometimes I give them induction that's not true. I don't say verify. I said check whether or not the given statement is true. So sometimes when I put equal, I realize that at the end is not equal, so just write not equal instead of. So you write question, not equal, because it wasn't equal.
That makes sense.
Right. Anyone writing this? Yeah, just you are Lafferin. You are not writing, so I guess Lafferin is not writing either. Right. Let's clear this. Number 3. What's number 3 again? Prove that root 7 is irrational. Nice. So this one for you guys must have been easy. Just looking in the book and write root 7 wherever I saw root, whatever I showed you before. Anyway, let's go through it. Since you're the only 2 here, you want me to go through it or you're good with it?
If you can finish the others in time, sure. Or if you want, you can leave that one for last then. Yeah.
Number 4. Okay. So we're checking to see the limit as n tends to infinity of that that statement is equal to a half. So n to infinity of n plus 2 over 2n plus 1 half. All right. So you know that our thing already is. Let me see if I can find that quickly. I always forget this thing out of my head. I think it's all n greater than or equal to m. I want to read it properly. Sequences. I have this thing written down somewhere. I know what, let me use this one. All right, so we need to show that all epsilon greater than 0, there exists an m. We're using capital M. There exists an m, which is natural number. So we want to find that m. So that for all m greater than or equal to, so for all n greater than that m, this is true now. The sequence minus the limit, absolute value of it, is less than epsilon. It's getting closer and closer to each other. No matter how small epsilon gets, it's going close to it. So you need to be able to find an m that satisfies that all the time. For any epsilon that you pick. So we need to find a special m. That's our first goal. Do some rough work, or as Lafferin called it, a little preamble. to find our m. So the sequence is n plus 2 over 2n plus 1 minus the limit, which is a half. So we're going to fix this up first to get n plus 2, and the LCM is 2n plus 1 and 2. Let's write the LCM from now. So we're dividing into 2 times 2n plus 1. So 2n plus 1 into that is 2, so it's 2 times this. Minus 2 into that is 2n plus 1, and it's multiplying the 1. So that's minus 2n plus 1. Of course, you need to bracket it. You're subtracting the whole thing. So that's now 2n plus, well, we have space, because this is just to find the m. So let's work it out. 2n plus 4 minus 2n minus 1. All over the same LCM. 2n's cancel, left with 4 minus 1, which is 3. So that is 3 over 2 times 2n plus 1. You don't need that 3 over 2. Pick it up. So this is the same as that. So that's 1 over 2n plus 1. This one looks like a 2 over here. So 1. 2n plus 1. Oh, it's got a 2, sorry. 2n plus 1. Now, because 2n plus 1 is a larger number than n. Oh, matter of fact, let's continue with this first. See, n has to be a natural number. It says for all. If you looked at from the start, it's just for natural numbers. So n has to be a positive number. So 2 times n plus 1 must also be a positive number. So we can stick to that absolute value. So this is 3 over 2, 1 over 2n plus 1. Remember I showed you before that you can always simplify the thing as much as possible. So you see, because 2n plus 1 must be larger than n, then this must be less than 3 over 2 times 1 over n. If I could have said less than 1 over n alone. You know, you like to keep little numbers in there. Let me continue this down here. 3 over 2 times 1. You can just write 3 over 2n, but anyway, leave it like this. This is what we want to be less than epsilon. Because I'm at this, let's go from the start now. We have shown that this right up here, this thing I start with, yeah, that is equal to everything right down to right here. So that first statement, the absolute value of a limit, was equal to everything right down to this. We didn't do anything, didn't put in anything or take out anything. Carry it all the way down to that. And that is less than the thing to the right of it. Because n is smaller than 2n plus 1, so the number to the left must be larger than the number to the right. And this now we have chosen to be less than epsilon. If we rearrange it, you're going to get that n, all of it is multiplied by the n and divided by the epsilon. They're going to get 3 over 2 epsilon is less than n. So the m that we are using is any number, or any natural number, larger than 3 over 2 epsilon. I need to put this on mute, you know. Okay, continuing now. So that's our m. Is anyone writing this, or you write this already again? I'm going to write fast, it seems. Or maybe not writing. Anyone writing? Or any questions so far? Sorry.
I didn't exactly do it that way, but just
fine.
curious as to whether the way in which I showed it, I used a video actually where they basically they did factor out the number.
They didn't factor if you were 2?
No, they didn't. No, but I mean, I'm seeing many videos in which they do it differently, right? In
Okay.
this case, they
There was an
factor out
actual
the,
video with this exact limit, or generally talking about?
no, man, generally, not the exact same
Oh,
question, but
because I
very
created this
similar.
question. If
Huh?
you told me that there was one like this, I created this, so if you actually phone one with it, I'll be shocked. That's made up this question.
Yeah, they did a very there's a similar questions. But the factor
Okay.
them out, what they do, they leave it as it is, and instead of and they would just drop off the plus. For example, you have the in factor it out,
plus
you'd
1.
have 3 over 4 n plus 2. So
Mhm.
they will put that greater than 3 over 4n. They'll take off the 2.
Oh, okay, that's what I mean.
Yeah, and then
Like right
work
here, they
work
could have done like 3 or, I mean, just put the 2n instead of 2n plus 1.
right.
Okay, that's fine.
So something like that. But so I'm wondering if all these different ways of doing it it's okay.
Yeah, man, because once you can find an m that when you put it back, it works out. That's fine.
You
Because
need
you
to get
want to
back
find
to
an m that works all
epsilon.
the time, you know. Yeah, right. Get that less than epsilon. Once you can
Yeah,
find a
that's
number
what.
that satisfies it all the time, that's good.
Yeah.
And you show it to
Okay.
me.
Yeah, that's why I don't really like this topic.
There are different ways, yeah. So I like, you know, what's one thing I love about math, you know? Math has one solution, generally. This now, all kind of different things like you see, man. So sometimes you're not sure which one to use, which one is right or whatever. That's the next like it as well. Wait. So this is our m that I'm going to use, 3 over 2 epsilon. It must be greater than that. Right, so m is any number, remember now. Let me write it down, I'm writing it. So now, we need to show that this thing, I'm writing the proof saying what we need to get, is less than epsilon for all n greater than or equal to m. All n greater than or equal to m. But what is our m? Any number bigger than 3 over 3 over 2 epsilon. All right, so let's go with that. So what is our limit? I mean, what is our sequence? It's n plus 2, n plus 2, come on, over 2n plus, forget it, hold on, is that correct? Yeah, that's it, n plus 2 over 2n plus 1. So minus the limit, which is a half, that needs to be less than epsilon. All right, continuing. At n plus 2, skip the step again. I mean, let's skip, but I forgot to write 2 first. Minus 2 times 2n plus 1. Where did I get 2 from? Minus 1 times 2n plus 1. You divide it into this LCM right here. Sure, whatever. That's still less than epsilon. So that breaks down to 3 over 2 times 2n plus 1, which we still want to be less than epsilon. Okay, that gives us equal to 3 over 2. Leaving 1 over 2n plus 1. Still want it to be less than epsilon. So let's go over here. Now we can take the total brackets out of the absolute value because it's a positive number. It has to be a positive number. Still want to be less than epsilon. But look at what is happening. 1 over 2n plus 1 is less than. Should I write that in one line? You know, let's write that in then. This has to be less than 3 over 2 times 1 over n. Why? Because 2n plus 1 is a larger number than n. We divide by a large number, it gives a smaller result. But that n we have shown was less than, we're going to use the n right here now. For all, remember we started at the start? All n greater than or equal to m. What is m? Every number that's bigger than 3 over 2 epsilon. So because n is bigger than 3 over 2 epsilon, then that means that 3 over 2, make sure I write it right here. Put 3 over 2 into. Because n is bigger than 3 over 2 epsilon, and that means that 3 over that number that n is bigger than must be smaller. Must be 2 epsilon. In here, yeah. Then that must be larger than that, because n is for every m bigger than that number right there. If you do the call it flip and divide and cancel and whatever, you're gonna say the 3 is cancelled. I'm not going to write it down. This is equal to 3 over 2 times this 2 over 3. Them cancel. I should have canceled them now. Where's the epsilon up here? Yeah. So the 3's cancel, the 2's cancel, that's left with equal to epsilon. And see, we had said it from right here that this, which was the original statement, I should use a red ink, this is less than this, which is less than this, which is equal to epsilon. That means that this first statement, the first underlined one right here, is less than epsilon. Is what I wanted to prove. So it doesn't matter what epsilon you choose, this m will make it less than that epsilon. Statement less than that epsilon all the time. So it is therefore limit is true, or it has been proven. Oh, Michaela is back. Is anyone writing this? You guys don't see anything, so I'm going to now clear it and do part B. So part B, this time the limit is of this sequence here, 3 minus 8n. So I want to show that it converges to negative 8. So as larger and larger and larger and larger, the sequence is converging to negative 8. Let's prove that. Once again, we do a little work to find out what is the m that we're going to use. This one is a bit more straightforward, as you will see now. But the reason I think that's because I just glanced through Lafren's work and it looked like it was simpler than what she did for this one. I didn't try it myself. Hopefully it doesn't give me any trouble now. So this is now 3 minus 8n over. So LCM is going to be n plus 2. And it's going to be minus minus 8 is plus. So this is plus 8 times 8. 8 not writing. 8 times n plus 2. The LCM is still n plus 2. That breaks down to, what's that now? 3 minus 8n minus 8n, pardon, plus 8n plus 16 over n plus 2, which is equal to the 3's cancel, sorry, beg pardon, 8's cancel, 8n's cancel, so 19 over n plus 2, which is 19 over n plus 2. Can we take note of the absolute value because n is a positive number, so everything there is positive. So the entire result must be positive. Now 19 over n plus 2 must be less than 19 over n. Why? Because n plus 2 is bigger than n. So that number must be a smaller number than 19 over n. Therefore, we're going to use that to be less than epsilon. Now, if 19 over n is less than epsilon, then that means that n must be larger than 19 over epsilon. That's the m that we're going to use. We're going to use m to be any number larger than 19 over epsilon. I said this one is more straightforward than the other one. Just drop the 2 when you get a bigger number. So I'm going to use that as m. Any questions or anybody writing? If not, I'm going to erase and continue. Anybody writing, man?
Sir,
So,
what if you flip it around? Would it work the same way? As in having n over 19 is greater than epsilon. 1 over epsilon. Yeah.
n over 19 greater than 1 over epsilon. No? Matter of fact, I've seen it done like that.
Huh?
Less than though.
N over 19.
Less than 1 over epsilon.
Well, let's say greater than epsilon.
N over 19 greater than epsilon?
Yeah.
I'm not sure that will work. I know if you use 1 over epsilon, it will work. I'm not sure if you use 1, if you use greater than epsilon.
Oh,
Maybe I can try that one time to see what happens. Where was I? Okay. So that's our m, 19 over epsilon. So you're just going to prove it formally now. The same thing as well. We're going to prove that as the sequence tends to the limit, as it gets very, very close, because epsilon is getting smaller, then there must exist some n. That's a symbol for there exists. I'm going to write the word. There exists some n which is bigger than m, which is an integer which is bigger than I'm going to use a while ago, 19 over epsilon, I think. 19 over epsilon. That makes that true. So it's for all epsilon greater than 0. I forgot to mention that. You know the proof already. You know the statement. For all epsilon greater than 0, this part right here, it must exist some n that's greater than m, which is greater than 19 over epsilon. That makes that true. Right. Well, this is for all. There exists some m. For all m greater than that. Anyway, where was I? Oh, proof. So now we're going to start the proof. 3 minus 8n over n plus 2 minus our limit must be less than epsilon. This to be true. Okay, continuing. It's going to be 3 minus 8n minus positive 8, so that's plus 8 times n plus 16. I'm skipping that step. Let's go straight to that. For n plus 2 less than epsilon. 8n's cancel, left with 3 plus 16, which is 19 over n plus 2 is less than epsilon. But 19, go to the brackets, because it's positive, over n plus 2 is less than 19 over n. Which is less than, use n to be greater than 19 over epsilon. So since the number, you know the explanation right there, I can't remember through it. So I have 19 over 19 over epsilon, which is equal to epsilon. So we have shown that this is less than that, which is equal to that. This is equal less than that, which is equal to this, which is equal to that. So from the beginning, we have shown that the original sequence minus the limit is less than epsilon. You know, some people just work straight across, like you work this equal to the top one equal to the bottom one, which is equal to the next one, which is equal to the next one, which is equal to that one, which is less than epsilon. Do like that as well. Because I'm actually writing this less than epsilon without proving it yet. But, maybe I should do that next time. Let me show what I mean. Show that this is equal to this, which is equal to this one here, which is equal to that one, which is less than this, which is less than that. So therefore, it's less than epsilon, because those two are less than epsilon. No. One of them is less than epsilon. Yeah, one of them is less than the next one, which is equal to epsilon. Yeah. Anyway, any questions?
No, sir.
All right. Anyone writing? No. All right, I'm going to prove number 3 now. Since you say if you have time, I'll come back to that. Oh, we have 4 minutes. Oh, Lord. Clear. Root 7. We're going to prove that root 7 is irrational. So, okay, we're just going to let it equal to a rational number then. We're going to prove by contradiction. I'm going to go a bit fast because of the time. Root 7 is equal to a rational number. Why is this not writing? Rational number, yeah. Where A, you could use the letters you want, X and Y. What the fuck, I should do this. I've gone bad already. Use X and Y. I was using X, I like using what we used to. X and Y. Where X and Y well, let me just say it since time is going, where x and y have no common factors greater than or equal, sorry, greater than 1. So x and y have no common factors greater than 1. So that's meaning it's in its simplest form. So we're going to let root 7 be equal to a rational number, where x, rational number x over y, where x, y have no common factors greater than 1. All right. So knowing that now, we're going to square both sides. So root 7 squared will be equal to x over y squared. I'm sure writing what I'm doing, so if anybody's watching afterwards. So 7 is equal to x squared over y squared. Multiply y squared by both sides. So we have that 7y squared is equal to x squared. Now, if the multiply rational, sorry, if 7 times y squared is equal to x squared, it means that x squared must be a multiple of 7. Because you see x squared is equal to 7 times y squared. So, in other words, 7 is a factor of x squared. Because if I say that 25, no, it was 25, that's so simple. It was 24. 24 is, quickly, is equal to 6 times something. Means that, so 6 times an integer, means that 6 must be a factor of 24. Okay, multiply an integer by 6 to get 24, it means that 6 can divide 24. So the same thing occurs with the 7 times y squared. If 7 times y squared is equal to x squared, it means that 7 must be a factor of x squared. And if a number is a factor of a square, correct that. If an integer is a factor of a squared number, it means that the integer is also a factor of the number without the square. I explained that to you the last time. So 7 is a factor, what a factor, right? So it's a right factor of x, but let me make sure I say it properly. 7 is a factor of x squared, which means 7 is a factor of x. Let's leave that space right here. I don't need much space to do this. So that means that we can write the x squared as a factor of 7, as a multiple of 7. So using that, all right, x squared was a multiple of 7. The different colors, this one, different things happening. 7y squared is now equal to 7 times, let's say, c squared. 7 times c, only squared. 7 times c. Because since x squared is a factor of, since 7 is a factor of x squared, f of x, then you can write x as multiple of 7. So since it was x and it's squared now, just replace the x with, I should write it like this. Therefore, x equal 7c. Making sure where that comes from. So we replace the x with 7c, squaring that, now we get 7y squared is equal to 49c squared. Remember, c is an integer. Divide both sides by 7, y squared is equal to 7 times c squared. Look at this. Now, y squared is equal to 7 times some integer. That means that 7 is a factor of y squared. Wait, but that means that 7, right, the same thing, is a factor of y. Okay, so 7 is a factor of y and 7 is a factor of x. That means that, wait a minute then, that means that x over y would have been simplified to 7 times something over 7 times something. Let's say p. But we already said that x over y was in its simplest form, where the largest number that could divide both the x and the y was 1. Now we have shown that this is a contradiction right here. From color geometry, you can write like this. Contradiction. Because it's a contradiction, it means that what we assumed to be true before, that root 7 it could be written as a rational number, was not true. The only thing we assumed, and it led to a contradiction, which means that what we assumed was incorrect. Therefore, root 7 is not rational, it is irrational. That is the proof. I've written that afterwards, but no space. How would I write it either? I tell you to write it. So because it led to a contradiction, where x over y was not in its simplest form, it's now simplified to 7 something over 7 something. A contradiction, which means that what we assumed was not true. Right. That's everything. 1, 2.
Number 1.
What is number 1? I told you to remind me after number 2, you know. I tell you what, forget. At 0 guys, that's every. Remind me after number 2 to go back to number 1. Oh boy. Right, I'll put the solution online before. I'll do it today, tonight. 2 o'clock. I'll do it at 2 o'clock. Because I have a class right now. So when my class ends, you all three if you have my number. But I don't know if Kida has it, but remind me please. My head not good. But 2 o'clock, send me a text or something. Call me if you want. Remind me to put the solution for number 1.
Do you want us to create a group and put you in it?
No, that means you ask me question every minute. But if I'm not in the group, you will be more weary about texting or calling. But I mean, don't feel free to come. You see, this class is small. I know you guys are decent students, so when you guys come, it doesn't matter.
All right, I'll give the other number if they don't have it.
I know Lafren has it. I don't know. I'm not sure if Michaela has it. Jermaine has it too.
Okay. Okay.
Michaela probably the only person who doesn't have it, if she doesn't. All right. So just remember to send me the reminder when I hit him in this class. Remember your test is Monday. I see you won't be seeing me. You just going to send the test on air. And
what the test is going to be on?
These stuff.
Okay, the same stuff with the assignment?
Yeah.
Okay. All right then.
But in fact, most of the exam will look like this as well. It's just that because it just have like 2 other stuff to do. The problem kind of long. Then 2 other topics left. So this one should be. We can actually finish everything before the first week in December. If I don't miss any more classes.
Okay. All right.
All right. See you guys Monday. Well, you won't see me. See me Wednesday. See you Wednesday. We'll see the test Monday.
Okay, sir. All right. Bye.